Hi, Mathletes. We're exploring the A value in quadratic functions. So after this lesson, you will be able to use the A value in an equation in vertex form of a quadratic function to identify the rate of change in the function.
The A value also gives us valuable information regarding a quadratic function's rate of change. We will now connect what we know to finding rates of change from tables to graphing quadratic functions. For 11, based on what you observed so far, what is the vertex in this equation? And when we put those in Desmos, we were seeing that this value right here is the opposite for the vertex, and this value right here was the same for the y-coordinate of the vertex, just like absolute value. So this is going to be -1, -3 for the vertex. Then it says the table below is for this function. And so you can see right here, this confirms that this is the vertex. So we're going to circle the vertex in the table. Part of how we know that this is the vertex is because we see these partner points right here, just like we did when we were graphing this in Desmos earlier. What is the A value in the equation above? So A value is this number right here in front. It's acting as the slope, and it affects our rate of change, and slope is rate of change, so that should make sense. And so we have a +2 there. Then it's asking us to find the rate of change in the table. So remember, rate of change is where we do the change in y and the change in x. You can see that our change in x is increasing by 1 all the way down. We're going to focus on our change in y. And from 5 to -1 is decreasing by 6. From 5 to 0 is 5, plus the 1 more to -1 is -6. Remember, you can look at your number line, which there's always a number line in every coordinate plane, so you can just refer to that. From -1 to -3 is going to the left 2 on your number line, so that's decreasing by 2. And then from -3 to -1 is increasing by 2, and from -1 to 5 is increasing by 6. So this should look familiar. Our rate of change is not constant, and if we recall for quadratics, it's our second difference that's constant. So let's take a look at our second difference, and that means we're just going to do that change process again with our change in y. So from -6 to -2 is increasing by 4, from -2 to +2 is increasing by 4, and from 2 to 6 is increasing by 4. This means that our rate of change in the table is increasing by 4. So our rate of change is not constant. This right here, change in y and change in x, is our rate of change, but that rate of change is increasing by 4, and that's what you are going to write here. So the rate of change is not 4, the rate of change is increasing by 4. And then it says, do you see the change in the equation? And so when we're looking in our equation, we do not see a 4, but I wonder if it's related to this 2 value that we see for A. And so my hypothesis is that our rate of change is equal to 2A. Because for this example, it would be 2 times 2, which is that increasing by 4. We'll see if that continues in our other examples. For 12, 13, and 14, I want you to do these examples. So what's the vertex? Circle the vertex in the table and answer these questions. Hopefully you can see here that your values matched with mine. Complete 13. Again, check that your vertex matches here and in the table, and that you can see that the A value is double the second difference. Complete 14 on your own. Again, look and make sure you're matching, that your vertex matches what's in the table, and that you got your second difference to be -2. Our A value, when there's just a negative in front, remember that is just -1 or -1 over 1. And we found that our rate of change in the table was decreasing by 2. So again, the rate of change is not -2, the rate of change is decreasing by 2. Let's go back and look at those tables and patterns. I put all 4 of our graphs on one page so you didn't have to flip between the 2 pages. I also added graphs to go with the equations, just so we can see the different representations, because I think that will help us. And so it says the first step is to look at the right and left, when I'm talking about right and left, I'm kind of visualizing the graph, and to the right and to the left of the vertex. When I say above and below, I'm referring to a table version of this when you write that vertical. So, if I'm going above, that's like going to the left on our table. To find the A value. So if I look at this equation right here, I see my A value is 2. And I can see that I have a +2 and a -2 here. That's what we call our first step, when we're plotting this. We plot our vertex, and our slope is actually up 2 over 1, up 2 over 1, just like absolute value, except for the next step is way more than that. It's not constant like it is for absolute value. So let me circle those things on here. So our A value is right here, and our first step is up 2 over 1 in both directions. This is a 2, and then in our table, you see 2 here. If I do the same thing on number 12, you can see that our A value is -4. We open down, and if I look at my graph, I'm going down 4, and to the right 1, and to the left 1. And you can see that in our steps here. And that plus or minus just tells you that you're going left and right for the 1. Again, for this question 13, our A value is 3, and you can see that I'm going up 3 over 1 and to the left, right and left 1. But it's 3 up, and I can see that 3 in each direction from our vertex. It may be helpful to circle the vertex. I only did that on the first one, so let me circle those here. And remember, you can tell your vertex by those repeat partner points. And on this last one, number 14, when it is just negative, that means our A value is -1. And I can see that I'm going down 1, right 1, and down 1, left 1 here. And I can also see that I have a +1 and a -1 in my table. So that's the pattern we're looking for. Now we want to look at the next value. Can we relate the next value in our table? So the 6 and the -6, or the 12 and the -12. Can we relate that to our A value in our equations? So how does this -6 relate to our A value? How does 12 relate to our A value of -4? How does -9 relate to our A value of 3? And how does 3 relate to our A value of 1? And hopefully you can see that 3 times our A value gives us that other value. So if I take 3 times A, so in this case, that would be 3 times 2, I get 6. And so plus or minus 6 are these values right here. And 3A for 12 is 3 times -4, or -12. And you can see that I have plus or minus 12 for the next one. 3A for 13 is 3 times 3, our A value is 3, that's 9, and you can see plus or minus 9 right here. And the last one, 3A, would be 3 times -1, and that is -3, and you can see plus or minus 3 right here. So we can use our A value to predict our steps. It's not constant. Once we do our down, like on this last one, to go down 1, right 1, we're not going to go down 1, right 1 again. That's going to be absolute value. We're going to go down 3 and right 1. And from here, we're going to go down 3 and left 1. That's really probably the only one that you can, I guess you can see it on the first one. You can go up 6. Oh, we're not quite there yet. And then to the right 6, but you can imagine that that's pretty close there. Complete 15, 16, 17, 18 on your own. Quick summary here. So this is our formula. It looks very similar to absolute value. If we're just missing the straight brackets, and we've added our square here to let us know that this is quadratic. The A value tells us if the U shape is going to open up or down, and it also tells us our steps away from our vertex. A value is the second difference divided by 2. Sometimes we just say rate of change, but we're ultimately in our table, we're looking at our second difference. Or 2 times the A value gives us our second difference, or how our rate of change is changing. The first step away from the vertex is always exactly what the A value is, just like it is for absolute value. But the second step away from the vertex is going to be 3 times the A value.